what I'm actually going to do now is shift to working with the example data that I sent you. The link in the instructions that I sent you, the document, should take you to this page here. And this is a page where the example data and code that I shared with you is stored. So if you go to this page and click the download, again, we'll be getting another zip file downloading. So if I go back to my downloads folder, oh, it's not quite finished yet. There we go. So this is the example data and code. So if I unzip that, I'm just going to leave that in my downloads folder for now for ease. And then hopefully you've all been able to, if you didn't already have it, install R and RStudio, I hope. But let me get that fired up myself. The next step is to start a project that will enable us to run the necessary analyses. So if I start a new project, I want to run it on an existing directory for the example, at least. So I'm going to browse to my downloads folder and the folder that I just extracted there, the example data and code. So I'm going to make that my project directory. And then create that project. Oh, I think you might be, I might have this on the wrong screen. Are you still seeing my my file explorer, I think? Is that right?
Yes.
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 Apologies. Apologies. Let me just rerun that. So now you can see my R.
Yes, we can see now.
Okay, great. Sorry about that. Just make that a bit bigger. So what I did there was once I'd fired up RStudio, I went to the File menu and clicked on New Project. And then chose to link that with an existing directory, and then browsed to the example data and code folder, which I just extracted from the zip file. So then I've already done that, so I won't do it again. Once I've done that, I click Create Project. And that now creates a project. So next time, you'll notice that back in that folder, this new file appeared called example data and code.rproj. So next time, if I finish my analysis for the day, I want to come back to it the next day, I can just double click on this project file in order to restart my analysis, and it will, if you saved where you got to last time, you'll go straight back to where you were with all of the relevant stuff that you need. So that's a useful way to run this sort of analysis. So to get going, if I click now on the Files tab here, you will see we've got several tabs. On the left, the main one here is a list of files. If I click on the Files tab, if I then click on the REM example.r, that takes me to the code we'll need to run to do the analysis. So now we've got an extra window on the window pane on the left, which shows us the code. And the output of what we run will appear in the bottom left pane. Okay, so anyone who's already familiar with R, forgive me for sort of going through some very basic stuff here, but I understand that's not everyone. So I wanted to try and make sure I bring everyone along from the basics as far as possible. So when you do this for the first time, there's a bunch of tools that we need that won't be available immediately within this analysis environment. So there are things called packages. So there are 4 packages here which we will need, called DevTools, Tidyverse, Activity, and Distance. So these are all crucial additional analysis tools that we need to install. And then CamTraptor, which is ultimately all of the functions that I've been creating to run REM analysis will be within CamTraptor. So you'll be able to simply run them from there. We're just still getting them down sort of integrated into CamTraptor, so they're not there quite yet, but they will be soon. In the meantime, they're already available, so you can start using them. You just need to load them in a slightly different way. So, but the main thing here is that when you're installing these packages at the top here, you don't need to do that every time you start a new analysis session. So this is just a one-off set of analysis that you set of installations that you need to run when you're first getting set up. What you do need to run before each session are these loading of packages. So this is done by running this function called library. So this, when you see this blue, this library function here in blue, it's a function, and then inside the brackets here, it's telling it what you want to run the function on. So library tidyverse means load the package tidyverse. That means that all of the functionality of that package will be now available in this session. Okay, so every time you start a new session, you need to run these. The functions for, as I say, the REM analysis are not yet wrapped within a proper package. They will be soon, but for now we need to load them using this line here. So it's just there is an online address that we need to point to. This is the address, so it's a subdirectory of the same one where we got the analysis code and functions, and the code for all of the functions we need is there, and will be updated if necessary as we get feedback on your experience of using it, and then ultimately will be wrapped into the CamTraptor package, as I say. Okay, so to run those, I can just highlight all of that. Then I can, if I hit Control Enter or Command Enter on a Mac, each of those will run. That all seems okay. Once we're up and running, red messages often mean errors, so that you don't really want that. In this case, we've just got some warnings that I think my version of R is slightly behind the versions where some of these packages were made. So it's just saying that might be an issue. In practice, it's not. So you can ignore all of these messages.
Sorry.
Okay, so before I actually run an analysis and take you through the output, I just want to mention that how the REM analysis works. So I think you've had some presentations on this, but I want to just give you a refresher so we understand a bit about what's going on inside these analyses. So the way that animal density is arrived at is through an equation that describes the relationship between density and trap rate, controlling for a few confounding factors. The first is that the size of the detection zone. If your detection distance, detection radius, and detection angle are bigger, for a given density, you're going to get more records. Similarly, animal speed of movements is potentially confounding. So if your animals move around a lot more, they're going to bump into cameras more, you will get more observations for a given density. So if we quantify the detection zone size, the radius and angle of the detection zone, and the animal's speed, we can actually use those numbers to quantitatively control the trap rate to arrive at a density estimate. So this is the reason why we need the animal position data, because we can then fit models to the animal speeds to get an idea of the average animal speed. We can fit models to the where the animals are relative to the camera in order to get an estimate of the effective detection radius and detection angle. Those estimates then feed into the control variable that tells us how to adjust the trap rate in order to arrive at actual animal density. Okay, hopefully everyone's at least a bit familiar with that, but that makes sense. So what the functions we're doing now fits those submodels for speed, radius, angle, also activity. So we break the distance that animals move across a long time span over the day on average. And we split that down into the speed whilst active, because that's what we see in the camera effectively, and the proportion of the day spent active. And the product of speed while active and activity level then gives us the average distance traveled per day, which is what we need for the REM control factor. Okay, so having said all that, the simplest way that I'm going to show you to run an REM analysis doesn't actually require you to engage with all of that submodeling. I'll show you a slightly more involved way that does enable you to do that if you want to get more involved and check that your models look good, and maybe adjust them. The line 19 here is the crucial line of code. So line 19 is the setup. So this is what enables us to read the data. So this is a slight modification of a standard CamTraptor function that's already available within the package. At the moment, we're just ironing out a problem whereby the function can't read the position data, the position and speed data that we need. So I've just modified it slightly to enable us to do that. I know that one person has contacted me to say this isn't working because the speed and other data that it's expecting couldn't be found in their data. I haven't got to the bottom of why that is yet, but if you have any problems, just get in touch and I can try and figure out why that is and get that fixed. But for the moment, if I just run that, we just get a message reminding us to make sure that we have permission to use the data. But if that's all we get, then that's not a problem. That indicates that we've downloaded the necessary data. So what's happened there is that I've used the read CamTrap dp2 function, and I've pointed to a folder within my working directory. So this is the working directory because my project is based within that folder that I created from the download zip file. Within that, I've got a folder called data, and there is a file called datapackage.json. So it's reading that, and it's assigning that. So this is an assignment function here that assigns it to an object called package. You can call that what you like. I could have called it Fred, or whatever, but call it something meaningful. So just call it package for now. If you want to, if you're maybe running multiple analyses on different data sets, you want to give it a name, give them names that are easy to remember and indicate immediately to you what those packages actually contain. Yeah, I just saw a question there about how where the angle comes from within Agouti. Yeah, that's right. So the model that we create using the pole digitizations then tells us something about the characteristics of the camera and of the ground, and those between them enable us to say for each point digitized where it is in terms of radius and angle from the camera. Does that make sense? So it's using a simple computer vision model based on those calibration images. And from that, we can calculate the angular and radial distances. Yeah, makes sense?
Yes, it is clear.
Okay, good. Okay, so we've downloaded our data, we've loaded it into R. So now we've got a data package. So this is in a particular format. So Agouti is working with a data standard, CamTrack DP, which because it is standardized and we know exactly what each column means, we can then run these sort of analyses, knowing exactly where to find each bit of information that we need. So it should be a seamless process to do this now. So in order to run an REM analysis, we have this function called REM estimate. All we need to do at the most simple level is provide a data package. So this is notice here, the object that we created called package. That's our data package. We just feed that into the REM estimate function. And here I've assigned it to a thing called result. Okay. So we'll look at the outputs in a minute, but first, if you just run this default setup without any other information given to the REM estimate function, if I just run that, what we're going to see is that we start getting some questions. R is asking us questions. So if we look in the bottom left, the console, it's saying use deployment. Do you want to use this particular deployment? And what we're seeing on the right are some images that give us some diagnostic plots about the fit of the deployment model. So what's plotted here is distance from camera, the radial distance model, as a function of relative Y pixel position. So 0 is the top of the image. We're going from 0 at the top down to 1 at the bottom. So 0 to 1, and then 1.5 is going off the bottom of the image. Okay, so you know, where the ground surface is coming away from the camera, the further you go away from the camera, so the further up the image, or the further down the image from the top you are. So the horizon is in a camera chat image. A regular deployment will be here somewhere, and as you go further on down the image, you're getting closer and closer. And this curve here describes that process. So we can see that the horizon is about where the curves disappear off the top of the image. And that horizon varies across, in this case, varies across the image laterally. So it's a bit higher on one side than the other. And you can see the points here are the points on the ground where the poles were digitized. Okay, and that is not a bad calibration model. So we can judge that because the points are quite close to the lines. We can see that there is this sort of downward trend that then flattens out as you get closer to the camera, steepens towards the top of the
Max, how do we understand the different cores? It's saying it's from the image left to the right edge. So what does it mean?
So so when you look at the image, you've got top to bottom, and you've got left to right. And if I'm doing left to right to you, you've got one side to the other, yeah. And if the horizon is kind of slanting like that, then you're going to get the curves. You get different curves across the image, right? So the horizon will be near the top of the image on one side and near the bottom of the image on the other side. So that's when you get separate curves. And just by default, the image is plotted with what goes on in the middle of the image, down the middle. The darker curve is what happens on the left, and the paler curve is what happens on the right edge of the image.
And to be good, this line should be close to each other.
No, not necessarily. Well, ideally, if the deployment has been done nicely, then yeah, the ground is flat and the camera is nice and perpendicular to that axis, then yeah, they should lie on top of each other. If the ground is really sloping and it's been very difficult to get the camera exactly right, then in reality, there may well be some variation, in which case a good model is one that has separate lines.
Okay, thanks.
Yeah. Okay, so that one is, I think, good. I'm happy with that. So I'm going to type yes and hit return. Then I get the next one. So that looks basically pretty good. There's maybe some issue here that there are some points here close to the camera where they don't fit so well. You might want to go back and check those. So it's possible that those are ones that were very close to the camera and it wasn't clear whether the pole was on the ground or not. So they may not be exactly right. I wouldn't worry too much about that though, because once you start getting into this area, you're getting relatively small errors. So ideally, you would go back and just check that the digitizations are good. But that maybe isn't too bad. You're not going to get huge errors in your distances for that deployment, even if those are a little bit out. Here's another one. It doesn't look too bad. Maybe there's not as many poles as you might like there. Ideally, you would have a few more, but that probably is going to give a reasonable estimate. So I'm going to say yes to that one again. That looks like a very tight model. I'll be very happy with that one. Looks like a very nice, easy deployment. That works out nicely. So I'm very happy with that one. So what this is doing is recording within the data package whether or not you reckon the deployment is good. If you've done everything you can, going back and checking the digitizations, maybe taking out poles that you're not happy with, maybe checking the heights, adjusting those if necessary. If you're left with only a few poles and the model looks really bad, then you can just say no, type an N and hit return here. And that model will not be used for the purposes, or that whole deployment will not be used for the purposes of any of the animal position data. So the speeds and positions won't be used. And you should be avoiding those biases. Okay. Makes sense.
Perfect.
Okay, good. Just checking the chat. Okay, so once I finish that, this is a small test set, so it's not a full-on survey, not a complete survey, but there's only
Marcus?
4 deployments. Yeah.
Can I ask a question? Now, suppose that you have 50 deployments, right? So a lot.
Yeah.
and then you find that there's a couple that are poorly calibrated, and you want to go back to those and check those. So you write down a little list.
Yeah.
I need to get back to those, and you go back. Then you go back into Agouti, I guess, and fix those and make a new export.
Yeah, yes, exactly. So sorry.
And then, but then you need to go through all these other ones again, I suppose, or can you in some way
Yeah, that's a good
keep
point.
that they are correct, or is there
At this
something?
point, at this point, you would need to just whiz through all of the ones that you know are good already. So
Okay.
I think this would be an obvious candidate where a graphical interface would make it much easier. You could save a potentially.
Okay. You're just checking. So
Yeah.
just skip them for now, and if you don't have enough, then you fix your data set and do it again, the whole thing.
Yeah.
Right.
Yeah. But I mean, it can be quick. I think once you get familiar with this, you'll know which ones you're looking for. Just to say that the title in the top left of the graph here, that's the name of the location.
Yeah.
Okay. So
Deployment.
yeah. So when I go back to, well, yeah. Just to make a distinction, which may seem subtle, but it's important, between deployment and location. In principle, it's possible to have, if you check your camera halfway through and the card's full and you need to replace it, you'll need to recalibrate that because you've moved the camera slightly. So that would be a separate deployment, but at the same location. So yeah, there is a slight distinction there. But within Agouti, if I just nip back to Agouti quickly, if you go to the browse menu here, it's actually the location name that you see them listed under. So that enables you to link between what you see in the graph here back to Agouti. So you can go straight to those ones and check the deployments. Okay.
Oh, and there's a question in the chat. Pablo asks, can you share one picture of each of these deployments? So SS3, SS4, etc. It will help to understand the plot.
For sure, yeah, that's a good point. I think that would be best done afterwards, or would folks we can take a look now if you want. I think it might be worth spending a little bit of time on that actually. So let me do that. So what I think I can do is up on one side. Yeah, let's do that.
And then another remark by Lexo, he says that the REM estimate requires the JPEG as a package.
Yes.
It's not in your script, but some people might not have it. So maybe that is important to add. Thank you, Lexo.
Yes. Thank you very much. That's a good point. Actually, that's yes. Yeah, no, that is important. So yeah, sorry, let me go back briefly to our script. If you see this list of functions here that you need to install here. So if you just add JPEG to that one, if you haven't already got it, that should sort you out, I hope. Thanks for that. Right, so so this is location 1. If I go to that, yeah, okay, so and then I go back to the annotations. So if I go to the sequence that contains the Oops, that's not what I wanted to do. All right, bear with me. Right, so if I use the sequence next button, I can go straight to that. Okay, so let's go with this one. So this is okay, so right, so we can see for this one, the ground is actually very obscure, so it was probably quite hard to get the camera set up perfectly here. The horizon looks to be quite near the bottom of the image. So a lot of, it looks about the middle of the image in terms of where the top of the grass is, but it's, as we saw, very long grass. So actually the horizon is probably somewhere much closer to the bottom in terms of where the poles are actually hitting the ground. So so we can see that, and also it was very difficult to make sure that the camera was nicely aligned with the ground surface. So we see that the lines separate out a bit. So that's how that looks there. If we then look at the next one, to go back to the list here. So if we go to the second deployment, we kind of got a night one, so it was quite difficult to see what was going on. I should say this is not, again, it's another horrible deployment. So this is a good lesson in how not to do them. This is some early deployments that we did with volunteers who were perhaps not as well trained as you'd hope. So we ended up with vegetation in front of the camera, and it's quite difficult to see what's going on. There were reasons why we were doing this at night, but in the end, it's probably best avoided if you can. Oops, didn't mean to do that. So so this is now the second one. Actually, that looks like it's worked out okay. So despite the difficulties, I mean, the grass in front of the camera is a problem for when we're trying to detect animals, obviously, but in terms of the deployment, it looks like that got set up pretty well. So, okay, 4. Okay, so that's pretty good. You can see a little bit of a slant in the horizon, which results in that slight separation of the curves there. What's going on with those points off the bottom? So those closest ones, I guess these are the closest. Yeah, so as we go further away. So these ones should be all right. Actually, this reminds me, there's one other point I wanted to make about this. What I've seen sometimes is that if you have multiple images of the pole at the same placement, so it's still sat on the ground, but you've got consecutive images with the pole not having moved across the ground, you only want to digitize one of those. There's no value in multiple digitizations of the same pole. So don't spend ages digitizing every pole every image of a pole that's on the ground. This one is actually slightly different, in a slightly different position, but it does look very much, we can see quite clearly it's short grass. It looks very much like that is on the ground. So probably any issue with those points not quite fitting at the bottom here is not to do with the poles not being on the ground. Maybe just simply that the model can't fit that so well in this case. But as I say, the error with that is not going to be so huge, so we can probably live with that. And then finally, the third one, what does that look like? So that's another nice short grass one. No real issues with that, nice level ground, but again, the horizon slanting, so that's why you see that separation of lines. So that's, you know, that's a situation where that separation is not a problem. The model clearly fits well, but it just happens to be the way the camera was set at a slight angle to the ground. So not a great, you know, could slightly improve the way the camera was set, but it's entirely usable as a deployment. Does that help, Pablo? Any thoughts on that?
Yes, Marcus, it helps a lot. Thank you very much. But I would like to ask, so in this plot with distance and relative pixel position, essentially, as we saw most of the points inside of the 3 lines, then it tells to us that the deployment is correct. I mean, we can use this plot in some way to validate or not, or to think that the calibration is done properly or not in some way. For instance, if we see all the points or most of them outside of the 3 lines, then we should review the calibration again, right? Yeah, that's right. Or if the 3 lines are look wild, sometimes you'll see if you have few points, or they're very contradictory. They're telling, you know, it's very hard to fit a well-fitting model. You'll see, you know, maybe you'll have one line that, you know, comes across the image here, and then another one over here. They're incredibly widely separated sometimes, and the points just don't seem to fit. They're either well outside those lines, some of them, 1 or 2 of them, or they just don't seem to correspond with what the lines are showing. That's a diagnostic that the deployment is going to be very poor. And you know, you should be able to also, if you match it up with the image, you can see that, you know, on the left-hand side of the image here, that's the darker line here, the horizon is slightly higher, and it's about a little bit less than halfway down the image. So yeah, that makes sense. That's all good. It's just a little bit over halfway down, or round about halfway down the image on the right, the paler line here. Yeah, that looks about right. So you can see that it's giving you a reasonable fit. Okay, makes sense. Thank you. Okay, so I think we are ready to analyze. So just to kind of emphasize that it's important to have a bit of an overview. So I recognize that this is not as simple as simply clicking a button, but with this approach, we can't really do that. We have to have some quality control on our distance estimation process. So we need to run through this. So this is an important step. So it's worth taking a little bit of time over, because it'll give you better quality data and better quality outputs. Okay, so if I go back to once you get to this step, the basic analysis approach, as I'm started to describe, is extremely simple. You just need this one function with this one input, the data package, which we downloaded. I've started running it. I've got the diagnostic plots run. Now there are multiple species in here. There's just a couple, in fact, a couple of hedgehog records and a few fox records, a few more.
and it's asking which species I want to analyze. So let's do the fox. So I want to run the second row there. So I type a 2 and hit return. It should start doing things. So this is an indicator that tells us that something's happening. This is just saying how far the model fitting process it is. Probably you will get some warnings and errors as you go through real data, but in this case, everything's fitted fine. It's been able to come up with estimates for everything, and it's been able to fit those models and come up with a density estimate. So I assigned that output. Nothing happens there. So this is the slightly scary thing about this sort of coding approach to analysis. But what I did was I used the assignment operator here to put the output of this function into a thing called result. So again, it'd be worth giving that a more meaningful name. I might have perhaps more sensibly called it fox result, let's say, because I chose the fox species there, but I'm just going to keep it generic for now. If I want to see what's in there, it's a data structure called a list, and the parts of that list I can see in RStudio if I type the name of my object followed by $, and then I get a list of the elements in there. So the main one that I've got here that we want to maybe look at first is called estimates. Okay, the other things are that it records the trap rate data that the density estimate was based on. It records the species, so if you forget what's in there, you can just check that element of the list. And it's got the constituent subparameter models, so the model for speed, the model for activity, the model for the detection radius, and the model for the detection angle. So let's start by just looking at the estimates. Actually, yeah, maybe we should do it the other way around. It may be sensible before you really believe and trust that the output of your density estimate, it may be sensible to check the models that go into it. So what I've done here, you can use this generic function plot to have a look at these models and just see how the data look. So if I plot the activity model, so result $ activity model. An easy way to do that is if you put a $, and then go down to activity model and hit return. That's less error prone than typing it out longhand. So if I plot that, we can see the frequency distribution of our records over the time of day and the fitted activity kernel, the model that's fitted to those data, from which we estimate the level of activity. So as you've seen, there's not much data here, so we're probably not going to get a hugely reliable result. Certainly there's going to be a lot of error, a lot of uncertainty around the estimate, so don't worry about that for now. But this enables us to check that the data look broadly sensible. The distribution, we know foxes are almost entirely nocturnal in this area, so we would expect all of our records to be during the night, so hopefully we can just check those things. Next up, we want to maybe look at the detection zone models. So the radius model here, we just need to add one little argument here. So this is a second argument to the plot function here. That's saying that we want to plot the probability density function and not the detection probability. So this shows us the raw data distribution, which I think is more useful for this model. There's some technical reasons behind this to do with the distance sampling process, which I'm happy to go into in more detail if people are interested, but maybe we'll leave that detail out for now. But just to bear in mind that if you want to look at the raw data distribution,
for the radius model, you need this additional argument when you plot it. So if I run that, so this is horrible plot actually, because we've got such a limited amount of data. So as we'll see, we didn't actually use all of the data, even though there were 15 or 16, I think, observations of foxes. Some of them just had a single image, or they didn't give us a good position estimate, so we didn't use all of them. So we've ended up with very few records here. We'll see that in the output in a minute. In fact, you can count them there, 2, 4, 6. We've only got 6 observations in the data there. So the plot doesn't look very meaningful, but broadly it is giving us some sort of sensible looking fit to those data, even though there's so few. It's never going to look great with so few records. So that would really not be a very usable plot. The part of the reason why we've got fewer records than we in this model than we had overall is because the data is being truncated. So it's assuming that it's not using any records over 10 meters away, or estimated distances over 10 meters from the camera. And that's broadly based on the fact that these calibration models tend to start performing poorly beyond that. Even where we have quite good calibration models, they don't do so well out to those longer distances. So we just want to concentrate on those shorter distances. So we've cut out those more distant records. The angle model, we can just run plot without the additional argument there. And that looks fine, that looks sensible. That's giving us a decline in angle that we might expect, slightly reduced detection towards the edges of the image. It's the way the detectors work. We don't have a plot for the speed model. We don't really need that. There's no kind of fitting it's of data distributions there. It's a non-parametric. It's just taking the harmonic mean. So we just have the values of that within the model. So there's no visual checking to be done there. It's worth just running those to satisfy yourself that we've got sensible models that fit the data. Similar to the deployment calibration models that I showed, really it's a question of checking that the data at least look sensible. They don't necessarily need to fit perfectly through the line doesn't need to fit perfectly through the data distributions, but it should at least give a sensible idea of the effective distance over which things are being detected. So apart from the fact that we have very limited sample sizes here, I think I'd be happy with those plots. So I think we're ready to look at our estimates now. So what you get if you run that is that this table of outputs. So you get estimates of the constituent parameters. So we get an effective detection radius of 2 meters in this case. We get a detection angle of 45 degrees, all told. Oops. We get an average speed of 1.5 kilometers per hour whilst active. Foxes tend to move around relatively quickly. They're pretty busy animals. And then we get an average activity level of about 25%, 247. We get a track rate of 0.23, 0.24 observations per day. Finally, we get a density estimate from that of just shy of 13 animals per kilometer. Okay, and then additional information here, we can see the standard errors for each of those. The CV is the coefficient of variation, so that's standard error as a proportion of the, or a percentage of the estimate. So that gives us an idea of whether this is a reasonably precise estimate. And then we see the units as well, just to be sure that we've got those right. Or we understand what we're looking at in terms of the units. The coefficient of variation is useful because we can quickly see here that this is a really terrible precision. 100% coefficient of variation means that really we've got very little basis for saying anything. The confidence interval for this would be sort of effectively somewhere between, I don't know, 0 and 50 or something. So extreme uncertainty. But that's obviously because we've got these very low sample sizes. So again, this is a toy example. So we'd be aiming for much better sample sizes, hopefully with at least some of your key species. Yeah, I think Pablo's got a question.
Yes. I would like to ask why the sample size for activity especially, but also for trapping rate is higher than for angle and radius?
Yeah, so okay, sorry. I should have explained that. The trap rate sample size is the number of locations. So it's the number of camera points that were in the data set. I know we had only 4. Sorry, this is confusing a little because there was I was working on this with the Agouti team, and they seem to have been putting some other folders in there which were not part of this example, so it ended up getting a bit messy. So there were some additional camera locations in there which didn't actually contain any records, but weren't part of this study. But so that 9 is that there are now 9 locations within that survey. 16 is the number of foxes that were the number of fox observations that we digitized.
But then
and then, yeah, sorry, the reason that the speed, angle, and radius are fewer than that is because what I was explaining earlier. So there are fewer speed ones, partly because some of those records are single points. Yeah, and we can't get a speed if we don't have 2 or more points for an observation. Also, there is some trimming. So extreme distances and extreme speeds are excluded. So there's some, essentially it's a process of identifying outliers, and it's done quite crudely at the moment within this. But we can, if you want to look at the effects of that, I'll show you in a minute how you can set up your own models and have different criteria for that. But at the moment, within that very simple single step analysis, you can there's a default. There are some default thresholds for defining extreme observations, and so those are the ones being cut out and not being used in the analysis.
Yeah, but theoretically, the sample size for activity should be quite similar than for radius angle. Not, I mean, for each individual. Yeah. Okay.
Yeah. If all of the observations are very close to the camera and well estimated, then yeah, that will be. The other reason they may be cut out is if you've maybe lower is if you've defined some observations that in that deployment model checking, if you define some observations as ones you didn't want to include, those observations will be cut out of the radius and angle models and the speed.
Okay, thank you.
Mm-hmm. Yeah.
Can I ask you, I suppose, Marcus, I suppose my question is connected to the second part of your presentation, but I didn't see here the behavior as a parameter. And when we are deciding the speed, I know the Pablo had such package trapping motion. Is it implemented here? And can we adjust the speed depending on the behaviors?
Yeah, no, this is not currently implemented. So this is something that I need to move on to think about. I think you and I should have a discussion about this, Pablo, in fact, about how to do that. Yeah, so we'll have to get back to you on that.
Oh, okay, thank you.
Yeah, there were some other questions.
Yeah, I had a question. I see that density is expressed in, I'm guessing, number of individuals per square kilometers. So just to confirm, this accounts for observations or sequences where you have more than one individual in the species. So like a family of wild boar, like select 7. So is it the average number in a group that is added to the analysis, or how does that work?
So there is no attempt to work on the basis of group size or group as the unit. So so when I originally published the REM idea, I did suggest that one could, or one should, analyze the group as the unit of density, analyze group size and multiply by, sorry, analyze group density and multiply by group size to get individual density. I've since realized that actually it's impossible to get a good estimate of group size in practice from camera data. Well, there's 2 problems. There's one is, in order to get group density, you would need to measure the, well, in terms of using the a purely camera-based estimate, if you were to try and get the detection radius for groups, you would need to be measuring the distance from the camera to the group center, whatever that is, and that's a very nebulous thing. And it's impossible to judge where that is from the camera information. So we're never going to get group density in practice. I think that and this is being recognized in other methods. So for camera trap distance sampling, the same applies really, that there's no sense in trying to estimate group density. What you can do is just treat each individual as the unit of observation. So yeah, does that make sense?
Yeah, but that gives me another question, because if we say we have a sequence with 1 female wild boar and like 3 piglets, if you're not counting them as a group, you then have to track, so give the position for each individual and throughout the sequence.
Yeah, that's right. You don't. Yeah, so that's a really good point. And I've been reminded to raise that. But it's really important that you do digitize at least once every individual that you see. So even if you think that it's not going to be a useful record, and for the purposes of radius estimation, for example, don't ignore it, because if you don't digitize it, it won't get picked up in the trap rate. So it should still potentially be included there. Although those,
Marcus,
yeah.
Do I get it right now that you're saying that the export from Agouti is telling you that you have 15 animals in a sequence? So you know the number of animals, but if you don't digitize them one by one, I mean, the model is estimating an average speed and an average angle for the set of deployments. Why do you need to have all those animals then tracked to get them into the calculations? Why is he not using the export of Agouti, which gives him all the animals?
I'm not quite sure what you mean. So you're saying that Agouti has a field that says number of animals. Is that right? Yeah, that's correct. But each of those animals has a different position at different times.
Yes.
So
but all the positions are used to calculate an average speed and an average angle. So you don't need. Do we then need for all those individual animals all the speeds? Because it's not using, I mean, the way you say it, you could use a subset of all the observations to calculate speed and angle. So why do we need to digitize all the animals if we have the total count? I'm a little bit confused now.
I was also thinking of the of Agouti, when you say that same example of the female with the 5 piglets. We would then annotate the female, which would be one observation, but then we would annotate the 5 piglets in one observation. But then for each observation, you can, in theory, the way Agouti works, if you can only track one of those piglets, not all 5, unless you do 5 observation of 1 piglet each time.
Yeah, and on top of this, Marcus, Agouti returns 1 angle and 1 average speed for every sequence, not for every observation.
No, that's incorrect. It's if we go back to Agouti, I think I'm right in saying. So if I go to if I go to this one. So this is a sequence. This is the first sequence of 3, and it contains 2 observations, each of quantity 1. So this is each of those observations within the same sequence will have a separate digitized set of points, and therefore different angles and radii. Yeah, does that make sense?
Yeah, that part does, but then if we have a quantity of more than 1, because we would then be annotating, say, vulpus,
you shouldn't
juveniles.
No, you shouldn't have that. So if you're processing for REM or distance sampling or any other of these types of processes, every observation should be a single individual.
Okay, so if you have 5 roe deer, then you have to have 5 observations. You can't group them based on age and sex.
Correct.
Okay, got it.
Marcus, I think we should, out of the course, we should discuss this again, because for me it's not clear, and I'm not sure that we're that it's really working like this. So, but it will bring us too far away if we have to discuss it through the end.
Okay. Yeah. Apologies, that wasn't clear. I think we have that was the solution we did, I think, agree on. But yeah, let's come back to it. But for now, that's the way the analysis has been set up. It assumes that every observation is for a single individual only. Okay.
Okay, for now.
Yeah. There's still a hand up somewhere, or is that an old hand? That's
an old one. Lynn, your hand has to go down.
Sorry.
That's okay. Yeah. Thanks. Right. Okay. So back to the R console. So if you want to check out some of the options on the function here, you can run this function called args, which is short for arguments. So that tells you what arguments are available. So if we look here, we can see that there's a couple of control arguments here. We can tell it to switch off the check deployment. So if we got it to a stage where we're happy with all the deployments and they're all good, we don't have to run through that every time. So we can just set that argument to false, and it'll just go straight into the analysis. If we want to supply our own models, we can do that. We don't have to use the default settings. So I'm going to show you how to do that in a minute. We can supply a text value for the species if we know what it is. It might be better to just let the dialogue show feed, because that way you're not going to get typos causing trouble. If it doesn't recognize exactly the right spelling, it'll be a problem. So that might be better. And the reps is by default, what it's doing is it's estimating errors for some of the values by running a simulation randomization procedure, which is quite computer intensive. If you want to run a model with lots of data that might take some time, and you want to just quickly get it running to check that things are working, you can reduce that number to make it run a bit quicker. But ultimately, to get reliable errors, you want to leave it on the default number. Okay, so to build the analysis yourself, so here's an example where I'm going to define the species that I want to analyze in text. So we're using the scientific name. This has to be the scientific name from that, specifically from the scientific name field. We can create an object called species that contains that text value. We can then fit our models, so we can fit the speed model. We can fit the activity model. So this takes a little bit longer. This is an example where the errors are being estimated by this simulation procedure. We can fit our radius model. We can fit our angle model. But crucially here, what I've done is I've got some different arguments here. So again, I'm not going to go into a great deal of detail here because that's really another session, but we're running distance detection function models here, which have some particular arguments. So we need to look at the help file for the functions that are taking these arguments to understand that. But we're using each of these functions here that fit a detection model, an activity model, a speed model. The angle and the radius are both using detection model, but with different slightly different arguments in this case. So I'm telling the function here that I want the unit to be in radians. I'm telling this here, this order argument is a more or less flexible detection function. I want to set that to a not so flexible one, because more flexible ones can fit better, but they don't necessarily give a better outcome. And this is saying I want to truncate the distance to 12 meters. So you can be more flexible here. Again, I'm not going to go into a huge amount of detail, but we can run more sessions on these if people need it, or you can look at the details on running the distance sampling models from the distance package if you want to understand what those arguments mean. I've got some plots here, but we've already run those, so we don't need to run them again. I want to get my track rate data. So there's a function here, get REM data. So that's for a particular package and a particular species. Again, so that argument goes in. And then I want to set up my parameter table. So that takes all of these models. So if you look back, these are the models that I fitted here. So we can use a simple REM function here. So all that this does is, so if I get my track rate data and my parameter data, just look at that. This is for each location, these are the 9 locations, the number of observations that we saw, and the effort. So this is the number of seconds that each deployment was run for. So we can see some very short ones. These were test ones. They were just set up, in fact, to calibrate cameras. So that's a separate issue. So once we've done that, we could go back to the one-step process. We could actually, if you remember, there were some other arguments there. We could put in the models to that, and we'll get a full output, or we can just run this stripped down version, and all that does is output the density and trap rate. So, but it doesn't have all the diagnostics there. Obviously, you can go back and use them in a stepwise way. So it's actually perhaps quite nice to use this one-step process, because you get a single object that contains all of the information that you need, including the submodels. Is that you got a question there, Lynn?
Yeah, just circling back to the arguments that you can give to REM estimate. The species argument, does it take more than one, a vector of length more than one? So if you say wanted to calculate it for 2 species at the same time.
Yeah, no, I'm afraid not at this point. That's not that clever. So that should just be a single name.
Okay, got it.
Yeah.
Thanks.
So you need to do it species by species. Jim?
Yeah, another question. Does the estimate of the radius and angle allows you to put in the habitat type at this level to model it or not?
You can do that within the you can't do that within the one-step process, but if you look here,
yeah,
the first input to the detection model is it's a formula. So if you're familiar with linear modeling in R, you'll recognize that as an R formula. On the left is what we're modeling as the outcome, so the radius. And on the right, I've got a 1 here, so that just means there are no variables predicting what the radius should be. If we have a habitat variable within our data package, we could type the name of that field within the data.
And would you because I mean the REM calculations become very useful if you have different speeds and different angles and depending on habitat types and also different densities, because you want to estimate differences in habitat use, for example.
Yeah.
Would you then recommend to split up the data, the package into
So at the moment
packages?
Sorry, go on.
Yeah, would that be the more easy stuff, to simply split up your deployments, make 3 packages, 1 for coniferous, 1 for deciduous, and 1 for open habitat, and then run?
Yes, at the moment that will be the easiest way to do it, for sure.
Okay.
So there is you could do that within I was thinking you could do that within R, but the easiest way is to create separate packages. I don't know how easy that is to do within Agouti. We might need people need to do that. We may need to come back to that.
It's pretty easy in R. If you use the constructor model, because it has the constructor package, because it has this predicates. Exactly. So you could use predicate to subdivide your package into 3 packages and then simply rerun the simple model, the simple approach in R.
That's
so
right.
It's definitely in R.
Yeah. So we can produce some examples of how to do that, perhaps.
Yeah. Okay. Perfect. Thanks.
Hi, Sterling.
I have 2 questions. One of these is to Marcus. Can we model, if we use, for example, 2 types of camera traps, can you model here the difference between their trapping rate, for example? Can you model the influence of camera traps on the density like this? That is how the radius depends on the camera trap, for example, or how the detection angle depends on the camera trap, because there are different models with different field of view and so on.
Yeah. So in this sort of environment, in this sort of approach, in practice, it's not strictly necessary to account for that. The reason being that if you have let's say you have two types, one of which has a, they're fantastically sensitive and you have a really good long detection zone, and the other is, very poor. The overall effective detection radius reflects the mix of cameras that you have and their relative sensitivity. So you don't need to explicitly control for that. In a sense, it comes out in the overall effective estimate in the model. So there's a concept in distance sampling called pooling robustness, which means that if you have different detectabilities, I mean, that was in the context of different observers being better or worse at seeing animals directly in the field, for example. It just means that you can have variation in detectability like that. But if pooling across that variation, the overall effective detection distance comes out reflecting that variation, and it doesn't create bias. So you don't need to explicitly control for it. But yes, in principle, if you wanted to check that, you could fit models with the camera type as a on the left-hand side of that tilde, the swiggle in the formula. On the right-hand side, and
yes,
the model would tell you whether there were significant differences.
Oh, okay, thank you. My second question is to Jim, because he was mentioning splitting the deployments in Agouti. Is there any easy way to split the deployments? For example, if you have tilted the camera, or some animals, for example, tilted the camera in the middle of your experiment, and is it needed to someone to look all the pictures from the first to the 10,000, for example, to see when was the moment of tilting, or is it any easy way for Agouti to split the deployment? Because, for example, I have one calibration at the beginning and one calibration after at the moment when I took the memory card. So if the camera was moved, for example, in the middle, can I split with Agouti automatically the deployments, or I need to see all the images again?
I'm afraid, Stoyan, that's really the nightmare scenario where the wild boar half of the month kicks in the camera, and then there's no automatic way at the moment, except if Patrick contradicts me, but at the moment there's no automatic way of having Agouti knowing what day the accident happened and how to bring it back. You will have to split them up to 2 deployments because it's 2 different calibrations for 2 different sets of observations. But no, there's no way of doing it automatically. I'm afraid, and it will be a burden. So I don't see at the moment I don't see a solution, to be honest.
Okay. Okay. Thank you very much. Thank you.
Yeah, I mean, it may be worth saying, just as a bit more looking further into the future. I do believe we will have better methods that are less labor intensive down the road, but they take time to develop. So in the meantime, we need something. So this is what we have for now. But I hope in 5 years the process will look easier.
Okay, thank you very much.
I think that's all I wanted to say. I mean, I hope this is going to be accessible to people. I know there's been some people have been able to run it. Others maybe have had 1 or 2 issues. But as I say, I'm here to help get over any initial problems or troubleshoot issues that come up, or other questions. Just get back to me. Are there any other immediate questions? Jim, did you have another point or question?
Yeah, if we still have some minutes, I wanted to get back to this this digitalizing each individual.
Yeah.
If I look at the model, the second part you showed to us, it's clear that it has this speed, activity, radiance, and angle to estimate, which you could do on a subset of data, on all the data you have. You don't need all the animals in all the pictures, so to say, because you're dealing with the first animal entering in the picture and the first distance and whatever you want. And then the trap rate, you can always assess on the count of Agouti divided by the number of observations. So I'm still puzzling with why would I need to have all the individual animals
Yeah,
being tracked?
the problem is that there needs to be some link between the data subsets being used and their positions, right? So a robust detection radius model requires some sort of truncation. But that also needs to feed back into the trap rate. So we need to know for each individual, you know, which records we're using for the trap rate. So if we're ignoring very distant animals, you know, we need to know you know, where they were. So there just needs to be that connection. Otherwise we're going to get mismatched data sets. So that you know, that selection goes on inside the process of fitting the model, but we need the information to be able to do that.
And did we already test what would happen if you would simply take the, let's say, the rough trap rate returning from an Agouti with the estimates, if it gives big differences on big data sets? Or it was not yet?
There isn't a formal test of that yet. I've done some informal testing, and yeah, it's I guess some mixed results, but yeah, we need some bigger data sets that we can test this on. I don't have a large selection yet.
Yeah, looking forward. Pablo.
Thank you, Jim. So in relation with your last comment, Marcus, what happens, for instance, if an animal enters, let's say, 15 meters from the camera, but then the animal comes directly or more or less directly to the camera at some point is, for instance, just 2 meters far away from the camera? Because, I mean, if the process in the function is discarding on the basis of the entered distance, assuming the random movement of animals, is quite probably that some animals at some point are closer than the distance in which they enter of the field of view. I don't know if I misunderstand something or you, I mean, or you have any idea about that.
Yeah, no, I'm not quite sure what the question is. Can you restate?
Yeah.
So I get the situation where an animal starts a long way away and comes towards the camera.
Yeah. So you discard, according to your response to Jim in your previous comment, if we discard those animals, for instance, according to the truncation distance for the radius, and let's say that you truncate at 12 meters, you will also discard this animal for the encounter rate or not?
Yeah. Yes. Yeah. Correct.
And yeah, but do you? I mean, I'm thinking now if it could introduce bias in some way, because the distance of the distance of the tension could be 12 meters, okay, but then the animal at some point is closer to the camera, and you will discard it.
Right, but for REM, just thinking about REM here, the relevant observation is the point at which the animal is first detected. So the distance there. So if you have an animal that is and the detection radius and the trap rate go in opposite directions. So if you discard a more distant observation, the trap rate goes down by 1, but the detection radius also decreases, and those things work in opposite directions. They cancel out effectively. Yeah, and it's just that you should end up with a more robust model that way. You see what I mean?
Yeah. I saw, but I'm still thinking on that. I don't see it very clear now, but thank you. Anyways.
Yeah,
Yeah.
the same for me. I have to rethink it because calculating EDFs, you don't throw away observations. You just recalculate them to another surface. So I'm also puzzled at the moment.
Why do you say you don't throw away observations? I mean, it's in the distance sampling framework that we're using. It's very common practice because the models can be very sensitive to outliers, so you can get poorly fitting models and ones that are less reliable if you include all the data very often. So it's generally good practice to remove those extreme observations.
It's clear to me if you're discussing about really far away observations, but with the camera traps, I have to see it if we start working with the data we have collected.
Yeah,
I mean,
yeah, I think that's crucial. Yeah.
Okay. I have to say thanks again, Marcus, for everything, because I will have to run in some minutes also.
Sure.
So it was very interesting and nice to see.
Okay, good.
Very much, Marcus, for your presentation, for your time today, but also for all your previous work before, which made possible that we are here today. So thank you very much.